Hi there. I want to start into chapter 4 today, which is about the use of organic chemistry. Right? In other words, what are the chemical processes that we use in organic chemistry? Remember, if this is where most of the chemists are working in the world, is in the field of organic, what are they doing? Right. So if we know from chapter 3 what the organic compounds are now. Right? We know alkanes, alkenes, alkynes. We know about substituted or branched chain hydrocarbons. Then we learned about the derivatives, the families, the alcohols, ketones, aldehydes, esters, amides, carboxylic acids, haloalkanes. So all the different families. And part of what we need to do in organic is understand how do we make some of these things, because some of them, they're not natural. They were never here before. We talked about some of them before, and we continue to move forward developing new organic compounds with new properties that we can use for different things. And I kind of like to come back to either new types of materials for foods, new types of materials for synthetics like fabrics for clothes. In some companies like Under Armour or Lululemon or the athletic wear companies, when they're making their materials, most of what's in their material is completely synthetic. It's something that never existed on Earth, and these companies have made millions and billions of dollars by developing and using these synthetic materials that have properties that make them really good for whatever it is that we're doing, whether it's athletic, being on a team or playing sports, or just being comfortable. Now, we know that there's a huge difference between one type of synthetic material and another, right? You can go and you can buy yourself a new shirt for running in, for working out in, and you could go and you can buy yourself a shirt for $10, right? Or you can go to a higher end athletic store and maybe buy an athletic shirt with a name on it that you recognize that maybe costs $60. You think, okay, that's a big difference, $10 versus $60. Again, if you're making $15 an hour, right, you work 1 hour and you got one of those shirts and change, and the other one you've got to work a 4-hour shift just to be able to, or a 5-hour shift just to be able to afford the shirt. So what's the difference? Right? Maybe you're just as happy in a $10 shirt, or maybe when you're using it, you're going to realize that there are some properties of the more expensive shirt that make it more desirable. Maybe it's better for what you're doing. Maybe it's more comfortable. Maybe it wicks sweat better. Maybe it breathes better. Maybe it stretches better. Whatever the case may be, maybe it's stronger. Right? You don't want something that's going to fall apart after a few washes. Right? So all these things come into our decision making about synthetic materials. So as we start into chapter 4 here, I think it's really important to just recognize how important this is, because ultimately we're surrounded by organics. I've been talking about them for 2 weeks now, and I think it's really important as we keep moving forward to recognize the importance of organics in our world. Now, like I said, we are organic. What we're wearing is organic. The food that we eat is organic. Our car, our bed sheets, our bed itself, our shingles on our roof, organic. And we get sick, right? We have organic, right? And then, like I said, ultimately, the whole industry of making food, not just cooking, but the actual processing and production of food to sell in stores to cooks and chefs and homeowners, right? That's a huge field of organic also. So it's important as we continue working along through organic to recognize that most of the organic compounds that we are working with today were never here before, right? We didn't discover a certain chemical, right? We've never discovered them. We actually had to invent them. We had to create them because they were never here before. Now, that being the case, if you're trying to make something that was never present before, again, that's got to make you a little bit nervous, right? Because sometimes when we do things that have never been done before, we don't really know what the long-term implications are. And we're going to see at the end of chapter 4, sometimes some of the chances that we take by discovering these things, by inventing these things, maybe outweighs the good that comes from them. Right, so not only do we need to invent them, but then we need to find a way to make them on a large scale, right? We need to be able to produce them in huge quantities that the world can use, the world can buy, the world can basically, it can be there for the world to use. So we need to talk about the different types of chemical reactions. You think, well, we know what types of chemical reactions are. Synthesis, decomposition, single and double displacement reactions, right? That's what chemical reactions are. When we come to organic, we've got very highly specialized reactions, such that we've actually come up with the names for specific types of chemical processes. And most of them involve things that we're going to be doing with hydrocarbons or with organic compounds in general. So we're going to look at one of the examples here. We're not going to be doing this, but if we were in class, we could make soap. Right? That's a saponification reaction. That's a chemical process that makes soap. And again, soap is something that wouldn't have been here before a couple of hundred years ago now, or maybe even more. And this whole idea of saponification makes a chemical that didn't exist before. We learned how to make it early, and it's worked very well for a lot of years. And there are still people who make soap. Right? There are my mother-in-law, my wife's mom, who actually passed away this year. Up until 5 years ago, she was still making her own soap. She didn't like the soap that she would buy for doing laundry at the grocery store. She found that if she used her own soap, it cleaned way better. And it was dirt cheap to make, and it cleaned way better than the Tides and all the other brands that are out there. So saponification, right? It's a chemical process that makes soap. Okay, so I'm going to look at a series of types of reactions, and we're going to look at what they are, how they work, and why we do them. What are the products? In other words, why are we doing something? We're doing it because we're looking for something. We're looking to make something or to get something out of a chemical reaction. So our first type of chemical reaction would be a combustion reaction. Combustion, we typically think of something that's burning. And when something is burning, what it is, it's a chemical reaction between the hydrocarbon and oxygen. That's what burning is, right? It's when something reacts with oxygen. So here's an example of something that's burning. I've got the hydrocarbon reacting with oxygen. It could be propane down here in my barbecue that's reacting with the oxygen in the air. And the products are three products. Well, really two products. The products are carbon dioxide and water. Anytime I burn a hydrocarbon or react it with oxygen, it's going to convert into carbon dioxide and water. So notice down here at the bottom, right, when I burn methane plus oxygen, I'm going to get carbon dioxide and water. Think, okay, that's great. So I've took some propane and I turned it into carbon dioxide and water. That's not why I bought the propane. I bought the propane for this, right? For energy, for heat, right? I want to cook whatever it is that I'm cooking on my barbecue. So even though energy isn't necessarily a product, it's also something that's going to be released when I have this chemical change going on. So if the atoms that are present on this side here are all present here, which they have to be. We know that. That's why we balance chemical equations. Right? I got 3 carbons here and 3 carbons here, 8 hydrogens here and 8 hydrogens. So you get the idea that the atoms have to balance, but then I'm looking more specifically for the production of energy. Right? So that's what combustion's all about. It's about reacting a hydrocarbon with oxygen to make carbon dioxide and water plus the energy. Now, when we burn something, we can get different colored flames. If I burn a hydrocarbon, so maybe it's a piece of paper that I'm burning, or a piece of wood, like a match that's burning, right? A wooden match or a cardboard match, whatever we're talking about. Maybe I just got a lighter, right? And the lighter contains butane, which is C4H10. We know butane, right? CH3, CH2, CH2, CH3, butane. When it reacts with oxygen, it produces carbon dioxide and water and heat. And I can use that heat to light my barbecue. Right? So if it's in my barbecue lighter, now when that flame starts, that flame typically is orange, right? And you think, of course it's orange. That's what color a flame is. Well, actually, if I had a really good flame, like a super hot flame, it wouldn't be burning orange. It would be burning blue. So the color that I want in my flame is a blue flame. And when it burns blue, that is going to be the hottest flame that I can get. And you think, well, yeah, but how do you get a blue flame when you burn a hydrocarbon or react it with oxygen? You're going to get an orange flame. That's what happens. Well, it isn't. If we undergo a chemical reaction in the lab where we react a hydrocarbon like the natural gas that's in our gas lines with oxygen, I will make my standard products of carbon dioxide and water, and I will get my energy. However, if it's not burning blue, now blue is almost an invisible blue. If you've ever seen somebody who's got a gas stove in their kitchen, I've got a gas stove in my kitchen, and when it's burning, I should be getting a nice blue flame. Now, if my jets on my stove get dirty, then my flame turns more and more orange. And what's happening is it's not burning as purely or as cleanly as it's supposed to. And the reason for that is because I'm having, incomplete combustion. So incomplete combustion tells me that there is not enough oxygen for the combustion reaction. So instead of every carbon picking up 2 oxygens, if there isn't enough oxygen, it's possible that some of the product could be carbon monoxide, CO. There wasn't enough oxygen to make CO2, and maybe some of the carbon just went off on its own and became solid carbon, which is the black soot that you get maybe at the bottom of your stove or your pot when you burn something on your stove. Right, so we've got 2 types of combustion reactions. Both combustion reactions are similar in that they involve a reaction of a hydrocarbon plus oxygen, but in complete combustion, I have only 2 products, and in incomplete combustion, I have the same 2 products, carbon dioxide and water, but I also have 2 new products, carbon monoxide and carbon. Now, one of the things about this kind of reaction is it's really hard to balance this chemical reaction because we don't really know how much of each of these things is going to be produced. Okay, I don't know how much carbon dioxide is going to be produced. I don't know how much carbon monoxide or how much carbon. All I know is I will get some of each of these if there isn't enough oxygen for complete combustion. Now that's what typically happens. If I don't have the right amount of oxygen mixing with my hydrocarbon, then I'm going to get that orange flame. It's not going to be that hot, and I'm going to make these 2 products here, carbon monoxide and solid carbon, which is black. Now, this yellowy orange flame that we're going to get is 1, not very hot. 2, is creating a lot of smoke because that black smoke that's being created is that solid carbon that we're talking about up here. Right? And then we're also going to get this thing here. Okay, carbon monoxide. Carbon monoxide is the silent killer. Right? It's a chemical that is in the room. If it's in the room, you don't know it's there. Right? You can't smell it. You can't taste it. It doesn't make you cough. It doesn't make you sneeze. You just don't know that it's there. You breathe it in, you breathe it out. The problem is, when it gets into your bloodstream, carbon monoxide looks like this, CO, and oxygen, which is in the air, looks like this. This is a good thing. This is a not so good thing, because when carbon monoxide gets into your bloodstream, it tricks your red blood cells. Your red blood cells are there to pick up oxygen from the air and carry it around your body. When there's carbon monoxide in your air, you're breathing it in, it binds to your red blood cells instead, and it prevents the oxygen from binding. So what that means is your body doesn't get enough oxygen. Your brain doesn't get enough oxygen, and what happens is your brain gets tired. And basically what happens is most people who are being poisoned by carbon monoxide, don't realize it, are basically just getting tired, and maybe they lie on the couch. Maybe they're already on the couch and the house is filling with carbon monoxide from whatever source it's coming, and we'll talk about sources in a minute. Once that carbon monoxide is in there, it just makes you super tired. And your eyes close, and that's it. Right? So it's a very peaceful way for a person to go, but most people don't want that to happen because you weren't expecting it. You didn't call for it. You didn't know it was there. You couldn't have planned it. It just happens. So the reason why people end up with carbon monoxide in their houses is typically if they are using something to create heat inside that's not meant to be burned inside a house or an apartment. And this happens every year. People die in Hamilton, in Toronto, in everywhere, in New York City, in London, England. People die when they get really cold and they can't afford their heating, and they will bring in some type of heater. Maybe they'll just get their barbecue that they've got that they typically use, and they just say, I'm just going to run this barbecue here for a little while and make some heat in this apartment. I'm freezing. I'm absolutely freezing. And next thing you know, as it's burning, it doesn't burn that clean. It produces carbon monoxide. And if there's a carbon monoxide detector in the apartment, it will start going. And if there isn't a carbon monoxide in the apartment, the people will go to sleep. And that will be it. And whole families die this way. Right? And it doesn't sound, it's not a gruesome way to die. But again, it's something that it's a real horrible situation when it happens. Right? So that's probably the number one reason why people end up with carbon monoxide. The other reason would be if they've got a furnace in their house that's not burning very clean. And if it's not burning very clean, then sometimes we end up with a bit of carbon monoxide buildup in our homes, and then silent killers there. So by law in Ontario, we all have to have carbon monoxide detectors in our homes. Now, I'm sure that as I'm saying this, not every one of you has a carbon monoxide detector. It's not a smoke detector, right? It's a carbon monoxide detector. I have both in my front hallway. I have a smoke detector in my kitchen and a carbon monoxide detector in my kitchen. I have a smoke detector in my basement and a carbon monoxide detector in my basement, and I have a carbon monoxide detector in my bedroom. Right? I don't want this stuff to get me when I'm not expecting it. Right? I have a gas furnace, like most people would. If you have a house, you probably have a gas furnace, unless it's an older house with radiators. And typically, that can be a reason why people end up with carbon monoxide in their homes. Okay, so those are two chemical reactions that we use all the time, right? Combustion reactions. What's what happens in your car? It's the reason why your car works. It's how we heat our homes. It's how we cook our food. Just on and on and on. All the chemical processes require heat. A lot of them use burners. Using electricity to heat things up is quite expensive, so we burn natural gas, we burn propane, we burn other things. But again, we just have to be careful about how we use that type of combustion. All right, so combustion, remember, a reaction between a hydrocarbon and oxygen. Two types of combustion: complete when there's lots of oxygen, incomplete when there isn't enough oxygen. Complete gives me a blue flame, which is hot, and I get water and carbon dioxide. Incomplete, I get an orange flame, which is a dirty flame that creates black soot. It's not that hot, and produces two extra products, carbon monoxide and solid carbon. Okay, my next types of chemical reactions are the opposites of each other. Just like synthesis and decomposition were the opposites of each other, we've got these two new types of chemical reactions called addition reactions and elimination reactions. Now, when I'm looking at an addition reaction, addition happens because I'm going to start with a compound that's an alkene or an alkyne. Let me get rid of that. I've got this double bond here. What's going to happen is this H2 molecule, or something which can be, I'm just going to say XY. It can be HH, it can be ClCl, chlorine, it can be BrBr, it can be HCl, you can see down here, it can be HOH, which we know is water, it can be any of a number of things. So when something comes along, and it's going to try and bond to that C double bond C, what it does, remember what's happening in this double bond here. In this double bond here is the carbons are sharing two pairs of electrons. Right now, what happens is there's a pair of electrons here, and there's a pair of electrons here. Remember, electrons are just two little negative particles. So the first pair of electrons doesn't like the second pair of electrons because they're all negatively charged. They'd rather not be together. Carbon would rather share its bonds with other atoms if they can. So if this HH hydrogen gas comes along, what it's going to do, get rid of all this, is it's going to come in and it's going to move in down here. It's going to move in below, and it's going to break the CC second bond, one of the two bonds, and instead break the HH bond, and then we'll end up with a CH bond and a CH bond. So let's make this bigger. Let me erase this and just start this again. So I'm going to take that HH, and I'm going to move it down here. Right? And then what's going to happen after I've moved it down from my other reactant, this bond here is going to break, and this bond here is going to break. And instead of carbon-carbon sharing electrons, the carbon will now share with the hydrogen, and the carbon will now share with a hydrogen. So what I end up with is my carbon with its two original hydrogens bonded to carbon with its two original hydrogens, and where I had a second bond here before, that's now gone. And now what I have is carbon bonded to the two new hydrogens. So I've broken the double bond, and I have formed two new CH bonds, and I've gone from this first molecule over here, which is ethene, right? Two carbons, ethane, but it's a double bond, it's ethene. And what I've now got is ethane, right? I've taken my double bond and turned it into a single bond by adding hydrogen across that double bond to both of the carbons on either side of the double bond. The same thing's going to happen down here, right? Get rid of this. So down here, I've got a carbon-carbon double bond, and here's my H-Cl. So the HCl is going to come along down here, and it's going to sit under the CC double bond. The carbon-carbon bond is going to break, the HCl bond is going to break, and I will end up with two new bonds, one from this carbon to hydrogen, one from this carbon to chlorine. So what I'm going to end up with is an chloroalkane. So let me just make this a bit smaller so I can draw it in. I'm going to end up with 1, 2, 3, 4 carbons. These are going to have the hydrogens that they had originally. So remember, originally I had a double bond in here, right? But now I've broken that double bond. All I have left is a single bond, and I'm taking the H from the HCl and the Cl from the HCl, and instead of the HCl being bonded together, they're now going to bond the H to the first carbon and the Cl to the second carbon. Okay, I'm adding something. Remember, addition here is like a synthesis reaction, right? Where I'm starting with two reactants and getting one product. If I look at my second reaction there, I've got HOH. What's going to happen is the H is going to separate from the OH. The H will bond to carbon. The OH will bond to the second carbon. So I'm going to end up with this first molecule. There should be an H here. There should be an H here too. I think I cut it off when I cut the diagram off. So I'm going to have my CH3. I'm going to have my CH. There was a double bond here. CH and then CH3 at the end. But then notice that my OH comes along from water, and I'm going to break those bonds between carbon and carbon. So I'm going to break that double bond and leave a single bond here. And instead, the hydrogen is going to bond to carbon and the oxygen is going to bond to carbon, and that's going to be, oh, that's an alcohol. I see a hydroxyl group on my butane, so that becomes butane with an OH group, which is an alcohol. That's butanol. Right, so I've now started with an alkene, which is but-2-ene. Right, but-2-ene. I've got 1, 2, 3, 4 carbons with a double bond after the second carbon, but-2-ene. And I'm now going to create butane over here. The double bond is gone with an OH, which means it's butane and it's an alcohol. Okay, so we haven't named them, but it would be butanol. If I look at the next example of an addition reaction, I've now got an alkyne. Here's my triple bond. It's an alkyne in that molecule. And I'm going to add H2 across that carbon-carbon triple bond. So let me erase this stuff over here. Okay, so I've got carbon, carbon, hydrogen, triple bond, carbon, hydrogen. What's that called? That's called ethyne. All right, CH, triple bond CH, 2 carbons. Now, the H2 is going to come along. It's going to line itself up under the triple bond. And then instead of having this CC bond, the third one, and the HH bond, I'm going to get rid of those 2 bonds. Get rid of this bond and this bond. And I'm going to create 2 new bonds. Got rid of 2 and create 2. Right, so I've gone from ethyne, to ethene. It's a double bond now. Oh, but notice that I had 2 H2s over here. So the second H2 is going to come along and line itself up with the double bond now. Remember, it was a triple bond originally, now it's a double bond, and I'm going to break those 2 bonds. Let's break this bond and this bond, and I'm going to create 2 new bonds. This bond and this bond. Oh, and look what I've got now. I've got ethane now. So I went from ethyne, which is what I've got on this side, to ethene when I had the double bond after adding H2, to being ethane now that I've added 2 H2s across my double bond. Okay, so those are addition reactions. For an addition reaction, I need to have a double bond or a triple bond. Right? Those are essential to be able to have an addition reaction, and I also need to have something that has got two parts, so I can add one side to the double bond and the other side to the second side of the double bond. Okay, the elimination reaction is exactly the opposite. In an elimination reaction, I'm going to take something like my hydrocarbon chain here, and along the hydrocarbon chain are two whatever they are, whether they're H and H, or H and Cl, or H and OH, and I'm going to remove them. When I break this bond, and break this bond, I can now allow carbon to form a double bond. Right? And the XY will form a bond, and it's going to take off on its own, and the C double bond C is going to form an alkene. Okay, so in order to have an elimination reaction, I'm going to form a double bond and form a second molecule because of the two things that I'm removing from my molecule that originally had a single bond. Okay, so notice there was originally a single bond in here, and I'm going to turn it into a double bond. So if I look at a couple of examples, if I take this molecule here, if I remove the H and the OH, they're going to come off as HOH, or water, H2O, and what I'm going to be left with is my CH3C with its remaining H, double bond, C with its remaining H2. Okay, so CH3, CH, double bond, CH2, propene. So I've started with my alcohol, my propane, which is an alcohol, so it's ending with OL, and I'm going to turn it into propene, which is the molecule on the right. I'm going to create a double bond plus my second product, which is water. If I take the molecule down here, I'm going to pull out the HBr. I'm going to do that by forming an HBr bond. And I'm going to form a double bond between the carbons. So I'll end up with CH2, double bond, CH2, or ethene. So I started with a haloalkane, a bromoalkane, and I'm going to finish up with HBr plus ethene. Okay, so those are some examples of elimination reactions. Okay, my last type of reaction here is kind of like a displacement reaction, and it's called a substitution reaction. Now, remember when I was talking about single displacement and double displacement reactions earlier in the course, I said sometimes we call them single replacement or double replacement. Something is replacing or substituting for something else. Here in organic, we actually call it a substitution reaction. So what we're going to see here is I'm going to start with my hydrocarbon with something attached to the hydrocarbon, and I'm going to bring in some type of binary molecule. Binary means it's got two parts. What's going to happen is I'm going to get a double displacement reaction. The X is going to replace the Y, and the Y is going to replace the X. So I'm going to start with a hydrocarbon that has an X on it, and I will finish having a hydrocarbon that has a Y on it. And where I started with AY, I'll now finish up with AX. So it's going to be a straight double displacement reaction, or a substitution reaction. But notice, as you're going to see in the examples here, I'm going to create a new family. So for this molecule here, if I look at this chemical reaction here, I'm going to start with this alcohol here, and I'm going to add hydrogen iodide. And what's going to happen is the iodine is going to kick off the OH, and it's going to join the ethane, and the OH is going to come off and join the H to make HOH, or water. So I'm going to end up with my two new products, which are CH3, CH2I, because remember the I has replaced the OH, plus HOH. Okay, those are my two new products. So I've changed my family. I've changed my alcohol, right? This molecule here, which was an alcohol, into a haloalkane, right? An alkane that has a halogen on it, right? Hugely different molecule, right? The molecule on the right is highly, highly poisonous. The one on the left is what you would have in a glass of white wine if you're drinking wine, right? Or rum or whatever, or beer, right? So there's a big difference between the molecule on the right that I created and the molecule on the left, which is what I started with. If I look at the second reaction that's on there, let me just erase what I've got on this one and make room for my solution. Okay, so for my second one here, this NH3 is actually an H, just like H2O. It's H coupled to NH2. And what's going to happen is the NH2 is going to come over and kick off the Br, and the Br is going to come over and replace the NH2. So what I'm going to end up with is HBr, because the Br came off and joined the H, right? The Br comes off the hydrocarbon and joins the H to make HBr, and the NH2 is going to jump up on top there, and that's going to make an amine. So I don't know if I've got room to write. I'm going to write it up here. CH3, CH2, CH, oops. CH, CH2, CH3, and on the bottom here, I'm going to have NH2. Right, so the NH2 that I had down here is now going to join the hydrocarbon chain, and I'm going to create one of the family, which is an amine. Right? Amines are molecules, hydrocarbons, that have an NH2 group on them. So we're now looking at how I can take some of the molecules, some of the families that I had before, and convert them into new families. So if I go back for a minute to my textbook, it's my textbook here. Oh, there's chapter 3. I don't have oh yeah, chapter 3 is fine. Okay, so we had all these families. Let's erase all my scribbling here. So we had all these families. I've got my haloalkanes, my alcohols, ketones, aldehydes, carboxylic acids, esters. And notice that we've done now is I've taken a haloalkane and converted it into an amine, or taken an amine and converted it into an alcohol, or taken an alcohol and converting it into maybe a haloalkane. So I can convert one family into another family, and by doing that, I'm creating molecules that I want. Out of molecules that I have, I'm going to create molecules that I want. Right? And that's what organic chemistry is all about. Right? It's about how do I start with a certain organic compound and use it to make the organic compound that I'm looking for. So today, as we're all home, one of the things that's happening as they make the announcement to close schools until September, right, which they just did today, or yesterday actually, when they make a decision like that, it's because they don't have a solution yet that allows us to go back to school. The question is, what solution are we looking for? Well, we're waiting for a vaccine. Right? There's no cure. Viruses can't be cured. Right? But what we can do is we can find a vaccine so people don't get the disease. right? If you're vaccinated against COVID, you'll never get it. It's not like you're going to get it and we can cure you. You just won't get it in the first place. So if I was to vaccinate everyone in Hamilton, no one in Hamilton would ever get the disease again, right? And that's what the vaccine's about. So the question is, how do you make the vaccine? Well, it's an organic compound. It's a little more complicated than what I'm saying, but basically we're going to take some starting ingredients and we're going to ultimately come up with a new organic compound that when I inject it into a person's arm, it will generate the immunity that we need, the protection against the virus, so that we're not going to ever get that virus. Right? So there's the beauty of organic chemistry. Right? The treatment for thyroid cancer, the treatment for prostate cancer, the treatment for lung or breast cancer, the treatment for Parkinson's disease, the treatment for Alzheimer's disease, right? All these different possibilities lie in organic chemistry, and people have spent their lives trying to find the organic compound, the magic molecule that's going to save lives. Okay, so I'm going to stop there. I'm going to leave you with, there are some questions here in the textbook, 1, 2, 3, 4, 5, and 6. They're in our textbook on pages 134 and 137 at the bottom of the page. And then there's some more questions. There's a bunch of them on page 142. On page 142.